Hello everyone, I hope everyone is safe and doing good. Welcome back to my channel Trick or Treat with Mathematics. So as the title of the video suggested, today we'll be saying about commutative property of whole numbers. So in the last video we have seen closure property, what it exactly means, and we have applied this concept on the various operations performed on whole numbers. Now we'll do the similar exercise, but we'll first understand what commutative property is in general, and then we'll go to the commutative property on whole numbers under addition, subtraction, multiplication and division. So before I begin, let me quickly show you this. What are these? These are a pair of socks. So how do you wear a pair of socks? Here I am wearing this pair of socks first by starting from the right, and then I'll go to the left and I'll wear the left sock. Okay, but sometimes I change my mood. I want to use the wear the left sock first, and then I want to wear the right sock first. Okay, what I have done is I have changed the order. First the left sock, then the right sock, and then first the right sock and then the left sock. But ultimately, towards the end of the day, I am just wearing socks. No matter what the order is, I can wear the left one and then right, or I can wear the right one first and then left. So this is commutative property. No matter what the order you perform the operation, you should get the same result. That is, left plus right is equal to right plus left. A plus B is equal to B plus A. A minus B is equal to B minus A. We'll see there is a restriction. A into B is equal to B into A. A divided by B is equal to B divided by A. Again, there is a restriction. So this is how you use commutative property in real life. No matter what the order, we'll need to get the same result towards the end of the day. It's also another, let me give you another example. We'll braid our hair, right? So if we wear pigtails, like small pigtails here, we can go in any order based on your feasibility, right? So we can wear the left one first and then we can go to the right one. We can tie the right one first and then we can go to the left one. But towards the end of the day, it's just you are braiding your hair. No matter what the order, we don't worry about the order as long as we get the same result. So this is the commutative property. Now let's see the actual definition of commutative property and its application on whole numbers. Let's see the commutative property of whole numbers under all the four different operations. So first, let's see commutative property of whole numbers under addition. So the commutative properties of whole numbers under addition means no matter what the order of the numbers that you add, the result should be the same. That means let's say take two numbers A and B. Okay. Here we are trying to prove that A plus B is equal to B plus A. This is the commutative property of whole numbers under addition. That means if you take, for example, A is 5 and B is 2. So we'll get 5 plus 2 as A plus B. That is nothing but 7. What is B here? 2. So B plus A as 2 plus 5. This is nothing but 7. So here the result is 7 is equal to 7. So that means commutative property satisfies for addition. Let's take 0. 0 and 3. Okay. So if we add 0 plus 3, we get 3. If we add 3 plus 0 also, we get 3. Right. Let's take one more example. 1000, 100. If we add 1000 plus 0, we get 1000 only, right? If we had 0 plus 1000, we get 1000 only. So no matter what the order of the elements are, we get the same result towards the end. So that is nothing but commutative property of addition. It means no matter how you add these numbers, you will get the same result. That is, no matter what the order is. So in short, we can say that A plus B is equal to B plus A. And this means commutative property is satisfied for whole numbers under addition. Okay. Now let's see the commutative property under subtraction. So you know that in subtraction we will take A minus B as the operation, and A is the whole number and B also needs to be the whole number. It's the same with addition also, right? So in subtraction we will try to prove that A minus B is equal to B minus A. However, this is not the case. Let's see why. Suppose for example here I'll take A, B, A minus B, B minus A. Okay. Now, what is A? Take some random example. 25, B is 12. What is 25 minus 12? You get it as 13. But what is 12 minus 25? You get it as minus 13. Is 13 equal to minus 13? No. That's why commutative property is not satisfied for whole numbers. It is satisfied when they are integers. Even if they are integers also, the value 13 and minus 13 is not the same. We are not getting the same result. So for integers also, it's not satisfied. So basically, commutative property is not satisfied for whole numbers when we are subtracting the numbers. Let's take one more example. 1000 and 0. What is 1000 minus 0? 1000. And what is 0 minus 1000? You get minus 1000. So 1000 and minus 1000 are not equal. Okay. So next we'll take one more example. 125 and 124. Okay. So what is 125 minus 124? You get it as 1. But what is 124 minus 125? You get it as minus 1. Here also the result is not equal. 1 and minus 1. If you observe 13 minus 13, 1000 minus 1000, 1 minus 1. The result is not the same. Hence, commutative property of whole numbers is not satisfied for subtraction. Okay, only addition, and now we'll see multiplication. It is also satisfied for multiplication, but it is not satisfied for subtraction and division. We'll prove the same in the later part of the video. Okay, this is the commutative property of whole numbers under subtraction, and make sure that you perform these operations considering this A or this B as whole numbers, and we use A and B as a terminology to represent whole numbers, as in just we are assuming that this is one whole number and this is one whole number. As mentioned in my previous video, these are just variables that we are assigning. Okay. So now let's jump to the multiplication. Now we'll see commutative property of whole numbers under multiplication. For example, let's take two numbers A and B in the same way as we have done before. And let's try to find out A into B and B into A, and then let's see whether A into B is equal to B into A. Okay, so this is a table that I just will make. Okay, now let's try. First I am taking 12 into 3. You must be knowing 12 table, and what is 12 threes? 36. And now I'll reverse the order. I'm still getting 36, right? So that means 36 is equal to 36. So commutative property satisfies for this number. Let's take some more combinations. 3 into 25. So 3 into 25 is 75. and 25 into 3 is 75. So 75 is equal to 75 and it satisfies. Now let's take 0 into 5. 0 into 5 is 0. 5 into 0 is 0. So 0 is equal to 0. It satisfies. What do you see here? What do you see the pattern here? One more number I'll take. 1 into 1. Just to maintain harmony. You're saying that no matter what the number is and no matter what the order we are multiplying, we are getting the same result towards the end of the day. So that means commutative property is satisfied under multiplication. Note that commutative property is satisfied for addition and multiplication. Okay. So that means you can say that commutative property of whole numbers will satisfy under multiplication no matter what the order of A and B are, provided A is a whole number and B is also a whole number. Okay, so this is the commutative property of whole numbers under multiplication, right? Now let's see the final operation of commutative properties of whole numbers under division. Now let's see the commutative property of whole numbers under division. So same scenario, we'll write it in the same way as previous. Okay, I'm saying that A and B are whole numbers, and I'll perform this operation and prove whether commutative property is possible for division or not. First, let's say 25 and I will be taking it as 5. Okay, what is 25 divided by 5? You get 5, right? But what is 5 divided by 25? You get 1 by 5. So 5 is not equal to 1 by 5. Am I right? So this is not satisfied for whole numbers. Next, suppose I take 24 and 3. Same case with this. 24 by 3 is 8. 3 by 24 is 1 by 8. So 8 is not equal to 1 by 8. It is not satisfied. Okay. Now let's see one more number. 1 and 5. What is 1 by 5? It is 1 by 5 only. What is 5 by 1? It is 5. So 1 by 5 is not equal to 5. So that means commutative property is not satisfied for whole numbers under division. That means even though we take A and B as whole numbers, if we try to divide and change the order of the division, A divided by B is not equal to B divided by A. How did we say this? Because the values are not equal. So this is how we prove that commutative property is not satisfied for whole numbers when we performed the division of whole numbers. So the order of division matters here. Okay, in brief, we can say that commutative property is satisfied for addition and multiplication, but it is not satisfied for subtraction and division. I hope you understood the concept of commutative property today. I request you all to please listen to the concept carefully in this video so that once you understand it, we can apply the same concept as we speak through the various numbers that we deal in the upcoming videos. So if you like my video, I request you all to please like, share and subscribe to my channel and ring the bell notification down below so that you will never miss an update from me. Till then, I hope you all have a safe day and a wonderful week ahead. The puzzle of the day and the previous puzzle solution will be following you right away.